All right, welcome everybody. This is a tutorial about how to use Unity. So the reason I wanted to make this was just to show you guys some good practices, some good programming practices, and things that are specific to Unity that really make it better and give you guys some direction when you're doing things. Because sometimes when you do things in Unity, it's kind of just random because you don't know why you have to do things certain ways. So I'm just gonna give you some pointers so you can kind of this won't solve all your problems, but this is the big stuff that I've run into in the last few years of using Unity. That if you look in the docs, they'll be like, "Oh yeah, I never do this," but nothing is enforced in Unity. Unity gives you enough rope to hang yourself. So I'm just trying to make that rope a little bit shorter so that you make good choices and make things performant and efficient. So these are a couple of things that you basically need to know if you're going to do Unity program, but this also applies to the .NET language in general. I'm going to talk about some things like the stack and the heap, which is not specific to Unity. A lot of programming languages use this framework, this idea. So we'll talk about how that works and why it's important to know. So yeah, especially in .NET, that's relevant. .NET, the whole thing is based on the stack and the heap. That's how the whole thing works. So good stuff to know. But you don't really hear about it in tutorials so much. You might have, but I'll just go into some detail. And then the second thing I'm going to talk about today is the profiler. The profiler is a really cool tool that no one teaches you how to use until you need to use it. It is just for it's for discovering problems. It's for finding memory leaks if there is any. It's for finding ridiculous memory allocations that you don't need. Just finding big problems. The profiler will tell you instantly where your problems are if you're having issues. And so as part of that, I'm going to talk about the garbage collection system that Unity has. And just how garbage collection works in general, and especially how it pertains to Unity, because there's some things specific to Unity that makes garbage collection a bit different, and you really need to understand how it works to get really great programs. And I'm going to talk about having a CPU and a GPU bound program. That's something pretty specific to Unity because most just standard applications on a desktop don't really need the GPU so bad. But definitely applications with visual parts, like games or especially VR programs, they'll use them pretty equally. And being CPU or GPU bound is a good thing to understand so that you can try to make your whole program more performant and keep those frame rates high. And then I'm going to talk about shaders. So shaders are just basically anything you see in Unity. It's got a shader that tells the graphics card how to put the pixels on the screen. That's what a shader is. It's a program. And the programming language that you use in Unity is called Shaderlab, and I'll give you a quick tutorial. I'm not a graphics programmer, but I've used Shaderlab a little bit. I've made my own shaders, and I'll talk about how to make shaders performant, and so you're not just randomly putting whatever you want in a scene. This stuff is really important to know to make performant programs. All these kinds of things are the kind of thing that will make the difference between your program running at 20 frames a second and running at 120 frames a second. Like, these things make huge differences. And you can tell if you go on the Unity store or you go on whatever Steam and buy some crappy game and people don't understand these concepts, you can really see the difference in quality, especially with frame rate. But these things will help you hopefully to improve that kind of stuff. So let's talk about the stack and the heap. So this is probably one of the most important things to understand when you're programming in Unity. Basically, all data in Unity is put either on the stack or the heap. They're basically, you can kind of think of them as they're places in memory. It fit like physically in your RAM sticks. So, but the long and short of it is the stack is good and the heap is bad. But there's a difference between these two. So the stack is statically allocated, and what that means is that you, like, if you've ever used C, you use like alloc and malloc and things like that. You allocate memory manually. So C# does that under the hood. It does those things in a slightly safer way, but the point is that they're static, so they don't change. You instantiate them, and then you deinstantiate them inside like some sort of a frame of reference. So it's really quick, it's really efficient, it's really awesome, but sometimes you want things that are a bit more freeform, or things that just don't go on the stack, things that are dynamically allocated. So at the bottom there, you can see like the different types of things in Unity that go on the stack versus the heap. So on the stack, you've got all your system.valueType inherited types. So you've got your booleans, your bytes, your chars, your doubles, your floats, your integers, all those other things you might not use, or structs. Structs are an important one. So all those things go on the stack. And the reason that the stack is good is because it's much, much faster, it's much cleaner, and the garbage collection system doesn't have to touch it. It's a perfect system if you want to manage your memory. Notice that the things that are not on the stack are things like strings, objects, pointers, delegates, and classes. So all those types of things, those are reference types. All reference types go on the heap. And so I think the main thing I want to stress here is that the heap isn't bad all the time, but what is bad is doing it, like using it too much, or not realizing you're putting things on the heap at all, and just putting so much crap on there. And the problem with C Sharp and Unity is that, like I said before, it gives you enough rope to hang yourself. So what I mean by that is, you can just put things on the heap all day long. You can put stuff that just piles things into the heap in an update loop, and it just does it every second. It'll put a gigabyte of stuff on there. But the thing is with Unity is that it cleans it up for you. It's got a garbage collection system that cleans it up so that you don't have to know how it works, but it really, really hits the performance really hard. And you can tell with crappy games, it's because they're putting too much stuff on the heap, or they're doing things that are just kind of boneheaded. But if you understand how all this stuff works, you can just get around that. It's easy. So like I said, the stack is fast and efficient, but it's not flexible. It is static. You put things on, you take things off, and it only works for certain types. And the heap is slow, but it is flexible. The heap is slow because it takes longer to put things on there. It is not. It's not in a perfect, like a stack is all. They're all bunched up next to each other and they're removed automatically. On the heap, it's just a big pile of memory. So when things get deleted, there's big holes. All these things cause issues. Also, stack. There's only one pointer to the top of the stack, but on a heap, there's a pointer to everything in the stack or everything in the heap. So everything has like you could think of it like an address. So it's almost like a dictionary of addresses, and all that stuff takes time to go through, and just makes everything slower. So you really, if you can, just use the stack. So the stack size is fixed at the start of a new thread, and it's just like I can show you an example of how it works, but and how to get around it. But we'll just talk about this. So, and something to note here is that modern CPU or just computer architectures are designed around this heap stack models. This is not something new, but it's just something to keep in mind when you're programming. So all that crap out of the way. Like I said before, the heap is actually good, but what is bad is unnecessary heap allocation. So that's what I'm going to talk about. So why is this important to know? So the heap is, if you can think about it, it's just a place in memory. When you start a Unity program or you make your own and you press play, a heap is generated. So let's say, for instance, it starts at 256 megabytes. Every time you put something on the heap, like let's say you're going through your startup section, you're loading levels and you're loading textures and you're loading shaders and all that good stuff that you need to have in your program, the heap needs to get bigger. And so what Unity does is it doubles the size of it. So that seems kind of weird. It's maybe not a big deal at low ends, but like when you get to, like, let's say 2 gigabytes of RAM, and you overflow on your heap, and Unity says, oh man, I need some more memory, it doubles it to 4, and that never gets unallocated. Now your program permanently uses 4 gigabytes of memory until your program stops. That's really, really bad. It's also very inefficient because a bigger heap means the garbage collector needs more time to go through it. So everything that you do to stop things going in the heap makes your program more performant. It makes the CPU work less hard. So it's just good in every way. There's really no reason not to do it. So here's a little picture. So we've got an int array. So that needs to go on the heap. It doesn't go on the stack. But you can see in this little white box here, there's not enough space. So what it's going to do is it's going to double the size of that white box to try and fit that in. But even if you later delete that array, and even if it becomes less than half the size, it doesn't matter. It's going to keep that enormous array and use ridiculous amounts of memory that the rest of the computer can't use anymore. So that's something to keep in mind. It's usually fine, but if when your memory use gets out of control, then it just makes your whole program really crappy. Something else to keep in mind here is that even if you're using things, that themselves don't make a lot of memory. Your um, your garbage collection system, which is basically, if you don't know what a garbage collection system is, on a stack, it's all managed one piece at a time. But in the heap, there's a system called a garbage collection system, which is, think about it like a garbage truck with a dude on it, and he has to go around to every house and say, "Do you have any garbage? Nope. Do you have any garbage? Yes," and then delete the garbage every single time. So usually a garbage collection system runs every like 2 to 5 seconds, and the more garbage there is to clean up, the longer it takes to perform. So the less garbage you have, i.e., things that you put on the heap and that you don't need anymore, the better. So in this example, I have, like, let's say you have let's say you're doing something in the update frame. So you have a 2 kilobyte thing. Like, let's say you make a list of strings, uh, every frame in the update loop. So you make a little string list, and then you don't need it anymore, because then the update loop ends, and when that reference frame is done, then that memory isn't needed anymore, so it's marked for deletion. So that might not sound like 2 kilobytes. Let's say is the size of that string array. That's not that bad, but if you consider that it's per frame, and the 60 frames per second, and the 60 frames in a minute, that's like 7.5 megabytes of memory per minute that needs to be cleaned up just for your update loop. So that adds up really quickly and just puts strain on your CPU. It just makes things run really sluggishly. I would say that heap misuse is probably the main reason why Unity engine games get a bad rap for being inefficient, but it's really only as efficient as you allow it to be. And so if you see a game the problem is Unity just doesn't enforce it. It doesn't. If you're doing things badly, it doesn't tell you. It just does it. It can handle it. It can do anything you want it to do. It'll just be slow at it. And so these games that you have, programmers that don't really care about putting things in the stack, or they're doing really inefficient things in the update loop, or whatever they're doing, it doesn't matter. It'll work, but it'll just run like crap. And so I feel like these games get a bad rap, because there's nothing wrong with the Unity engine. It's just as efficient as any other engine. It's just how you use it. Hey. Yep. I'll just... Yep. Oh, yes. Yeah, Unity is just as efficient as any other programming language, framework, game engine. It's all the same. It's just how efficiently you want to spend the time to program. So what can you do about it? There's lots of things you can do, and you can look it up. Um, okay. Does anybody have any questions, by the way? We can have some questions later, but if you guys want to jump in with a question on something specific, just go for it. Uh, like pointer as in this stuff here. So on the stack, or with one on the heap, or one on the stack, or just in general. So pointers are always um, they're pointers are reference types. So all reference types go in the heap, is basically what I'm saying. So these are just two lists. Like, whenever you instantiate a class as an object, it always goes on the heap. Objects always go on the heap, and that's fine. You just want to limit how often that happens, um, and yeah, I don't actually know. Yeah, go ahead. Sorry. Oh, sorry. Sorry, I misunderstood your question. A pointer is like, think of it like literally like a pointer. Like, instead of um, let's say you have a big file like a picture, and I say, hey, hey Mac, check out this picture. If Mac's a program, I can say, hey, and then literally give him all the bytes to that file, which would take a long time and it's really crappy. Or I can just give him a pointer to that file. I can say, hey, look at this file. It's really big. I'm not going to copy it byte for byte, but I'm going to give you this tiny little piece that just points to a place in memory, and then you can check it out yourself. So it doesn't copy the picture twice in memory, which is what you sometimes do have to do. But like in this case, you just want him to look at the same picture that I'm looking at. So it's just a way to save memory going around unnecessarily. You just have a pointer to an object, and you can just pass that pointer around. So if you say, like, you do it all the time without even knowing, basically in C#. Usually you're working with pointers. Like you're pointing. Sure. Yeah, so usually things in C# are just passed by reference anyway, unless you explicitly say, like, literally pass all the data, like, manually. Go ahead, Vivip. Yes, exactly. So you can run into issues if you don't understand the difference between passing by reference and passing by value. So it's kind of out of the scope of this. I didn't really want to talk about that, but that's definitely something to be aware of. Almost always in C#, unless you explicitly ask for it, is passed by reference if it's an object or something like that. So if you so let's say for an example, oh, maybe I should do a code example. Maybe that'd be good. But if you have like a program and you have a parameter, the parameter you're passing is by reference usually, unless you explicitly say pass by value. You'll be passing a reference to it. So if you modify it, you're modifying the original one. Anyway, um, yeah. Yeah, for sure. So yeah, pointers are fast. There's no question about that. It's much faster than copying it. The point isn't that pointers on the heap or even the heap that is a problem itself. It's just when you allocate things on the heap that really don't need to be there, then it makes the whole heap slower. So if you just add a bunch of crap onto the heap that you maybe didn't need in an update loop or something that could be done a lot less often that's happening every frame, it's just going to pile the heap with crap, and it's going to make everything in the heap run slower because every index operation in the heap is just going to take longer because there's more indexes to go through, basically. So there's not really a problem with pointers specifically. I probably should have raised the pointers in this because the point of this picture was I found it from a different thread, but I just like the picture to describe the difference between the heap and the stack. But pointers are good. The point of that is that pointers are just one of the types that end up on the heap. Like pointers cannot be put on the stack, or I guess they kind of, by example here, can. I don't know what the hell that's going on, but pointers are a reference type, so they always go on the heap. Is my point. Does anybody have any questions about that? Okay, perfect. Um, maybe it'll become clear in the examples here. So what can I do about the stack and the heap? It's a problem. It's maybe difficult to understand what goes in the stack, what goes in the heap, but what can you do about it? So here's a concrete example of recycling. So using something again. So in the first example, it's an update loop, just like in Unity, and you're at the beginning of the update loop, which usually happens once a frame, so 60 times a second. We've got a list of a float, and we're making it. So it's a new list. We're making a brand new list, and then we're find distance to nearest neighbors, and then we're doing a sort, and then we use the list somehow. So that's all fine, but the problem with this is that every time we make a new list, even if it's in the same update frame, we make a new list, an entirely new block in memory in the heap every single time we go new, for example, because list is an object type, it's a reference to an object, and so we use the new keyword. That means make a new pile of crap in the heap, which is fine if you do it once, but this is happening 60 times a second. So what's happening there is that we're making a big giant block in memory, just like in these examples before, but the problem is we're not using it again. This makes a new one every single time we do it. So the garbage collector has to go around and clean all these up every frame. Or not every frame, it doesn't run every frame, it runs every like 4 or 5 seconds. But if we have like 600 lists just sitting in the heap, like something's got to clean those up. And so it's just going to take longer for the garbage collector to run. So as a solution to that, what you can do is you can do something that's pretty simple. Just put the list, just instantiate it at the start of this class. So it's still in the heap, but it's only used once, like it's only instantiated once, and it just stays on the heap for the lifetime of this object. And then we just use it over and over again, and we just clear it every time. Pretty simple. It doesn't take any more lines of code. It's just thinking about how the heap and the stack, or specifically how the heap uses memory and how the garbage collector is helping you. Like the first one will work just as good as the second one, except much slower. They'll both physically work, but the second one is much more efficient because you establish one object and you keep it for the lifetime of that object, and you don't have to make one every frame. So that's something you could do. Just recycling parts, recycling objects, having one, having like one public or global function inside this class, and just using that instead of generating one over and over again. So what you also can do is watch out for boxing. So boxing is a little bit of a complicated topic, but I have an example here. You'll notice this is a whole bunch of stuff, and as part of that stuff, it says, so if you remember from before, if it's an integer or something like that, that's put on the stack, and that's true. So you can have a really efficient little program that uses integers, and they're put on the stack, and then when the reference frame is gone, they're removed from the stack. And that doesn't go on the heap. It's really efficient. It's really nice. But if you do something like this, in this for loop, you'll notice that there's a for loop, and inside of it says, if things I does not equal null. So that's a problem, because things like integers and all those other data types that I mentioned before that go on the stack don't have, like, null isn't a property of those things. If you ask if they're null, then what C# does under the hood is it takes that integer and then turns it into an object and then says, is this object null? So that's a huge problem, because you're basically taking this perfectly fine performant program and turning integers, which are value types, they go on the stack, and then you're forcing them onto the heap. So total waste of resources. This is just something that's specific to this, it's not specific to C#, but it's a problem that you'll see. But just be aware, I guess the takeaway from this is that all those value types, like floats and integers and characters and booleans, all those things, null is not a property of them. If you ask if they're null, the compiler is just going to say, okay, turn this into an object, then ask if it's null. And all objects go on the heap, so it's kind of undoing all your work that you're doing. So something else to watch out for is that you might have noticed that strings are not, they do not go on the stack. They go on the heap. That's usually fine, except not, because strings are horribly, disastrously inefficient. They are inefficient for a couple of reasons. One of the main ones is because every time you modify or concatenate or do anything to a string in any way, it makes an entirely new string, and all of those strings go in the heap. So if you just say, it doesn't matter what you're doing, if you're doing string literals or anything like that, every time you modify or change a string, it goes in the heap. So if you're doing it inside something that happens really often, like 60 times a second, it actually does take a lot of memory, and it all has to be cleaned up by the garbage collection system. So just be aware that strings all go on the heap, and they're not very performant. Integers are performant. That's fine. You can do those in for loops. Floats less so, but they still go on the stack, but strings do not go on the stack. They go on the heap. So every time you use a string or change it in any way or make a new string, it makes an entirely new string. So just be aware of that. And also be aware of string literals. I know I talked to Kalesh and Mac about using things like a string literal is literally when you put like quotation marks and you put a string in there. Like in this example, I've got Judkins. That's a string literal. And not only is that a separate thing in memory, but also that's a permanent thing in memory. They like C# actually permanently like puts that somewhere. It's permanently as part of the program until the end of the life cycle of the entire program. So if you have a whole bunch of them, they're gonna permanently have a memory overhead. They'll never get deallocated. So that's really strange, and just be aware of them. So you should try and avoid string literals unless you got a good reason for them. What you should do is you should have some external file and then load strings in with the external file, because then when the file stuff is deallocated, then all the memory gets put back. But if you use literals, they're never put back. They're stored for the entire life cycle of the program. So I guess the takeaway from this is just limit the amount you modify and create new strings. Like for example, you could make a UI that updates 60 times a second and just hard sets the text even if it hasn't changed. But the problem with that is every time you do that, even though it's the same thing over and over again, you're making a new allocation on the heap. So that's really inefficient. So you could do something like, why not only when something changes? Like have an event system that says when something changes, then update the text instead of doing it every 60 seconds. It might not seem like a big deal, but it really makes a huge performance increase when you do stuff like this. And just, even if you don't refactor all your code, just programming in the future and taking these sort of things into consideration really just helps your programming game. So this is a specific This is a specific example of a function that you can use, because things like equals, like if you're comparing two strings, is really fantastically inefficient. And so my recommendation is to use this exact piece of code here. So if you can say, my string, so let's say like my string up here, first name plus Judkins, and if you go dot equals is to compare two strings, and then you have your other string. But what you can also do is you can add a second parameter to this equals function and say string comparison dot ordinal, and it's like literally orders of magnitude more efficient because it's a bitwise comparison program. The regular equals it takes things like localization in different languages into consideration, but if you're just using ASCII characters, it's totally a waste of time to do that. So you should use, little shortcuts like string comparison dot ordinal as another parameter when you're comparing strings. Just be aware, even if you don't remember all of these things, but just be aware that strings are really performance heavy, and if you do a lot of string manipulation, it's worth taking a look into some of the good practices with strings, because they will bite you. They are nasty, and I've run into these problems too, professionally and in my personal project work. So what else can you do? There's a cool thing you could do called object pooling. See, all this stuff is really simple stuff, and thinking about how you're gonna build something really just makes it more performant out of the gate. You don't gotta come back and do all this stuff, gut all your code and do it all over again. Having these things on your mind just helps you code better, so you don't have to go back and fix things that are incredibly inefficient. So let's say, for example, this could apply to any object, but let's say we make a particle system that makes sparks, just like this picture. Ignore that there's a particle system in Unity. Let's just assume that we're going to make it ourselves. So my first thought would be to create and destroy a spark, 8 times a second and throw them in random directions. That's all cool, but if you make an object and destroy it, it takes a lot of performance to create and destroy, and also when you destroy, the garbage collector still has to come around and clean it up. So you're still instantiating these things in memory and then destroying them, and then the garbage collector's got to clean it up later. So that adds up really quickly. But a better thing you could do is just have a pool. Like let's say you have 40 sparks and you instantiate them all at once, and then you just make them appear at the center and then do their thing, and then after a lifetime of 5 seconds make them disappear and then recycle them. Don't delete them or instantiate them. Just have them always there and then just turn them on and off. And that is way, way more performance efficient on the heap, because now the heap doesn't have a bunch of sparks that is made 40 times a second. It's just got this set, and it doesn't have to delete anything. As long as the sparks are in the scene, it'll use the same amount of memory permanently. That's a typo. We instantiate once on the heap is what that should say. So, and that stays for the lifetime of the sparks. So that has a huge impact on the memory usage and the CPU performance. So those things go hand in hand, because if you use lots of heap memory, it probably means that the garbage collector is going to be using a lot of performance to clean up all your crap as well. And you can use this tactic in code too. I've used like a pooling method, where if you need a bunch of objects to do something and you know how many you're going to need at any one time, just make a pool of them and then just reuse them instead of destroying and instantiating them over and over again, like that previous example. With this is kind of almost like pooling. You're kind of having a pool of one single list, I guess. Not really a pool, but there's one single list. You're just using it over and over again. It's all part of that recycling idea. So those are some cool things you can do to get around using the stack, or get around using the heap and using the stack instead. Yeah, there's a lot of stuff in there to talk about, but I think that kind of gives you an idea of how all that stuff works. It's a big topic, so you should definitely also look it up on your own and just find out the details and look out the technical stuff and what exactly goes in the heap and what doesn't, all that good stuff. But I think this gets you started. So I'm going to talk a little bit about the profiler now. So the profiler is like a metal detector. It will smell the horrible things that are going on in your program. So it's basically like a graph, but it also has like a little section to measure the memory usage of all the parts of your program, so you can dig down and find out the specific things that are using a lot of memory or using a lot of CPU stuff or a lot of whatever. It'll help you for GPU stuff, it'll help you for CPU stuff, it'll help you for memory, all that good stuff. And you can break it down into different parts, like is your physics doing it, is your animation system doing it, is it your garbage collector, all that good stuff. So it's a fantastic tool. I suggest you use it early and often, but people sometimes don't talk about it, but it really is so important for making your program performant. The first thing I want to talk about with it is the garbage collection system. So the profiler notices issues with the garbage collector, and I've run into this problem really big time at one of my previous companies, and we had to learn how the profiler worked because it was just so helpful. It was just like, it was a lifesaver once you figure out how to like use it properly and often. You'll notice I've got a little picture down here. That's the graph, and I've turned everything off except for the garbage collector. So I'm just looking at what the garbage collector is doing, and you can see that, you can't see for reference, but there's a 4-second gap between this little spike here that you can't quite see because it's under this white bar, and then this little spike over here. These are just the garbage collector stopping the entire main thread and sorting out all your memory problems. And this was not a big program that I had this running in. This is lower than what I would say typical. And you can see that it's got a number of milliseconds. So 4.21 milliseconds a frame, depending on what your frame rate is between like 15 and 25 milliseconds. So that's a pretty significant portion of your frame is just spent on cleaning up your memory. And so what that actually does to a program, you might have played games or something that every few seconds it'll like lag for a little bit, it'll drop a few frames, sometimes it'll go to like 10 frames a second and then it'll go back to 60, like in regular intervals. It's because of the garbage collection system. It's because something is getting instantiated and the garbage collector's got to sit down and clean it all up, or else you're going to run out of memory. So this is a really good thing to keep an eye on, because it can definitely get out of hand really quickly. And also a cool thing about the profiler is that it's got like a little breakdown thing, and I'll show you when I do some Unity examples. I'll show you what it looks like. But basically, you can dig down into specific things, like the player loop is the overhead one, and then you can dig down and find out exactly what is using all your resources, how much time it's taking, how much memory it got allocated in that frame. So like, look at this thing. I am in this program, log string to console. I'm using debug.log. Like, look how much memory that's using, just in one single frame. It's probably using it every frame. So that's probably why my garbage collection system is working overtime and giving me like 5 milliseconds of latency for one frame. It's because it's got to clean up crap like this. So This doesn't solve your problems. It won't find out every bug in your program, but it definitely tells you where to look because you can sort it by how much memory it's using, how many calls it's making to the GPU. Like these are pretty reasonable. 2, 1, 2, 4, 1. That's a pretty reasonable amount of calls, but I've had programs working at other companies where it'll be in the hundreds of calls. Like something is making literally 200 calls to the GPU. Like no wonder it's lagging. So it's like it's really easy to see where the problems are happening, and you can see just at a glance. You could be like, well, this is using 5 kilobytes. That's not too bad. But if something's using like 85 megabytes in a garbage collection allocation, like that's pretty insane. That's all coming off. That's going on the heap. Whatever that is, probably shouldn't be happening too often. It's hopefully that it just happens once. So then you can just go into that. You can dig into it. You can find out what you're allocating, and then try to do it once instead of every frame. These are the kinds of things that when you get to like a profiling performance part in your project, this profiler is absolutely like invaluable. There's nothing. I don't know even how you do it without something like with a tool like this. So the next thing I'm going to talk about coming off from that is that programs, you might have heard something like CPU or GPU bound, which basically means what's the bottleneck. What sort of things are bottlenecking your program? And quite often in the life cycle of developing a program, it'll jump back and forth because as you work on your performance, you use your profiler well. You'll find that there's problems on the CPU, and then you'll improve the CPU performance. You'll cut out those things that are doing ridiculous things, and all of a sudden now the GPU has to catch up to the CPU. The GPU is slower than the CPU because how this works is that they're both getting. I don't know if I have an example, but in a frame, like let's say it's in this 4-second frame, there'll be a bunch of tasks that both of them have to do, the CPU and the GPU. They both do different tasks. The GPU is a specialized processor for doing certain type of math, like calculations, things with geometry and shaders, all that stuff. It's really performant at doing those types of tasks. And so when the frame starts, or let's say the frame's getting prepared for the next frame, the CPU has a bunch of tasks. It's got a bunch of physics, and it's got a bunch of probably your code is probably a lot on the CPU. And then the GPU has also a bunch of tasks. Usually it's the shaders. Shaders are usually what tells the GPU what to do. So if you have a bunch of complicated shaders and volumetric shading algorithms and reflections and stuff, and your fancy car is using it's taking longer than your CPU, then you're CPU bound. So you can see down here that this program that I have running here, it's 8 milliseconds on the GPU and 20 milliseconds on the CPU. So it's very clearly a CPU bound system. But it can go either way. If you get crazy with your shaders or you get sloppy with your shaders, this goes up really quickly. It doesn't take long for a shader to take up a lot of time to do. Because GPUs are powerful and amazing, but they can't do everything. You really have to do a lot of tricks and have a lot of knowledge to make them really perform well. And these are the kinds of things that I want you guys to think about. This doesn't just apply to Unity. This just applies in general, is to think about this kind of stuff. But to give you an example of what stuff is CPU and what stuff is GPU bound, typically all the code that you write is on your CPU. Like anything you write in for loops and all that stuff, basically 99% of that is all on the CPU. I don't even know how you do it on your GPU. So all that stuff is done on the CPU. Things like pathfinding, things like moving things, transforming things, all that stuff is done on the CPU. And then the CPU gives the GPU instructions on how to render that. So it moves things on the CPU, like moves things around the scene, for example, and does all the code and the loops and all that stuff. And the GPU is controlled by shader scripts, and the shaders tell the GPU which pixels to put up there. So if you have lots of graphics and large textures, fancy particles, those are the types of things that it's going to bog down the CPU because all those shaders got to run all their operations before the scene can be done, the frame can be done. So not a whole lot of things to say about that. Basically, it's a ping pong game. You optimize the CPU, then the GPU is lagging behind, then you optimize the GPU, then the CPU is lagging behind, and you basically try to get that down as low as you can. And really, really good quality software, they go through many, many iterations of this process. And they use things like profilers to make sure that their programs are performant. This is especially important in things like VR, where you need to maintain a certain frame rate to be comfortable. If you start dipping frames, people start to get sick. So it's the most important thing to maintain frames. Yeah, it's done automatically. I don't know. I know there's ways to give tasks manually to the GPU. I don't know how to do that. That usually never comes up. Usually you'd never want to do that because unless it's unless it's a big task, like if you like a task that's repetitive and just needs a lot of computations. But the problem is that the GPU is a separate processor, yes, but the things that is in your memory, that's in your program, has to get there, right? So the CPU has to actually take it to the GPU. So it's better if it's things like that are really intensive, but I can give it an instruction set, like here's a texture, here's a shader, shade this thing in 1080p. That's more efficient. But like things like doing for loops and doing regular programming stuff and moving transforms, it would have to take the code from memory, send it to the GPU, get the stuff back, whatever that is, and then it would have to move it back to memory anyway. So there's like a two-step process. It's just not really built to use the GPU in that way. So typically most things are the CPU, and things like graphics are done on the GPU. But if that kind of makes sense, I think you can use the GPU for certain tasks. Like you can force the GPU to do certain stuff. I don't know how to do that. That's beyond my ability. I've never had to do that. Hmm. Definitely. And just like the thing with the GPU is it's a specialized processor, where a CPU is more general. Like it can do a lot of different tasks, but maybe not as fast as a GPU. But a GPU is made for specific tasks. It's got because like CPUs have like logic circuits for like addition and subtraction and multiplication, all that stuff, and GPUs have those same things, and they have specialized ones for certain types of calculations. Um, so like their architecture handles how those things are done. But if it's like Mac was saying, I don't know an example, but like matrix operations, they have special circuits for doing those types of calculations. And floating point operations, I know they're amazing at. That's why, because like they use a lot of floating points for doing whatever, rendering textures and like surface shaders and things like that. So they can really quickly pump out a lot of floating point arithmetic faster than a CPU can. So they're good at really specific tasks, but they're not a general CPU. So most things are done on the CPU unless you have a really specific task like matrix math or something like that that's really heavy, and it's worth spending the time for the CPU to send all the data and then receive it back and put it back into memory. It's kind of like it's that kind of a trade-off. But definitely people do it. I'm not sure if it would be appropriate for a game, but you definitely could. That's a pretty advanced topic. I've never done that personally, but I'm sure you could. But so going into that, let's talk a little bit about shaders. Shaders are important because if you are GPU bound, like we were talking about before, it's probably because your shaders suck, I would guess, or you have too many of them, or they're doing too many things, or something like that. So shaders are basically programs that tell your GPU what to do. They tell your materials how to behave, is what they specifically do. So every time you see like particles or surface shaders or anything like that, shadows, it's a shader that's telling it's telling the GPU how to do things, basically. So it uses a different language. It's called Shaderlab, and I'll do a little example of a quick shader today. I'm not a graphics artist, but I'll tell you I'll tell you what it looks like, and then you can be brave and try some shaders yourself, because shaders are seriously one of the coolest things once you get used to them. They can do some absolutely amazing things that you really just would never be able to do with a CPU bound program. And it's like sometimes like it's really incredibly easy to do things that seem so complicated. So the cool thing about shaders is that they work exclusively on the GPU. GPUs are, like I was saying before, are optimized for these types of tasks. So whatever you do is usually pretty performant. Like if you were going to try and do the same thing on your CPU, it would take a lot more time. And so just in general in Unity, there's shaders, but you also might have seen materials. Maybe you don't understand the difference between them or what their relationship is. Think of a material like an object instance of a shader. So a shader takes in, and I'll show you how this all works. It takes in variables like what texture you're going to use, maybe some floating points, some vector 3s and vector 4s and all that stuff, maps and all that stuff. Those are all the variables, and then it puts it into a little quick program, and it runs however that magical program runs, basically. So you'll have logic gates and things, so you can just turn off different parts of the shader. But basically, a material is just an instance of that shader. So the shader with a specific texture on it is a material. And you don't put shaders on objects, you put materials on objects. So a shader is just how the code works in the back end. And then a material is like an instance. So if you want to put a brick wall on there and you want it to be really shiny, you have an instance of a shader called a material, and you put a brick texture on there and you make it really shiny, and then you apply it to that surface shader of that object. I'm sure some of you understand how that works, but that's kind of how a material works in relation to a shader. So you might have seen in like in Unity, if you put just a box or a brick wall or whatever, it'll make a shader for you, and it usually says like standard or something like that. So those are like your general shaders. They'll do everything. They have all the maps and all that stuff to do basically anything you want, but the problem with them is that they don't perform that well. They're very inefficient. So if you're doing them, like they're more for getting prototypes running is really what they're for. They're not intended to be used in production code with a professional team. You'd make custom shaders for everything in your scene because it's just too expensive to have general shaders, because general shaders can do everything, but the problem is that they do everything. They can have albedo maps, they can have bump maps, they have normal maps, they have all these maps, and they have all these little settings and offsets and all this stuff that you maybe don't need for most textures. So it's just a waste of time and a waste of GPU processing time to like render and have all these options and make all these calculations when it's really just not necessary. So it's better to just write your own shaders and just cut out the stuff you don't need. So in my experience, that's a lot of what I have done, is just make shaders exactly what they need to do to make them as performant as possible. Yep, so big companies don't use stock shaders. They build their own. And the people that do that are technical artists or graphics programmers. There's probably a difference between them. I'm not either. But I have worked with them, and they're amazing. And they make your life so much easier. Because they just handle all the graphics and performance stuff, and they're responsible for all that. But we don't really have someone in our team that's like that. That's like a dedicated graphics programmer. But it's a cool thing to have if you have it. So the name of the game is, with all graphics performance optimizations, is ask yourself, what can I get away with? That's what you should always ask yourself, because it doesn't matter if you have an 8,000 by 8,000 pixel texture. If you're 800 feet away from it, you don't need to render that many pixels. So it's all about what can you get away with. How performant can you make it while still looking basically the same without impacting the visuals of it. So that's what graphics programmers are really good at, getting away with doing a lot less but having the same result. So that's just something to think about. So that's what Shaderlab looks like. Thanks, Mac, for getting this picture. That's what it looks like. Just a bunch of code. It looks very different from any other language, but the syntax is fairly simple. I don't know a whole lot about Shaderlab. I can do some stuff, but this is something that a dedicated graphics programmer would do, and you really have to have a lot of knowledge on how a GPU and how GPUs work in general to be able to make really, really complicated shaders. But you can do simple shaders and modify existing shaders just fine with no expertise. Whoops. Absolutely. Now, Shaderlab is built right into Unity. So Shaderlab is just a language. So I'll show you. It's just like a CS file, except it's just a .shader file instead, and it's got the same code. It gets compiled the same way when you compile a Unity project. So I'll actually, I'll show you exactly how it works. So I've got a little program. This is one of the games I'm working on with my brother. This is just a test scene that I'm doing some cool programming stuff in, and I've got this toilet. I thought that'd be a good example because right now it's got a shader on it. You can see at the bottom it's got a shader, but it just says standard. This is just the one. If you just drag a random, if you just have a random mesh, you can just put it in a scene. It by default uses the standard shader, and some people just leave it like that. Like they'll just go, "Yep, that looks good," and they'll change the color, and they'll make it cream colored, and that's good enough. Good enough. But the problem with this is look at all this stuff in this shader. This is really complicated. You've got albedo, metallic, normal maps, height maps, occlusion maps, detail masks. These all have switches, so if they don't exist, they don't happen. But the smoothness and metallic things, it's got emission. If you want to have an emission map, it's got tiling and offset. It's got secondary maps. It's got forward rendering options. All this stuff is part of the program, like a Shaderlab program. So this is really complicated. The cool thing is that you can put any of these things on in a flash. You can just like add a metallic map or a normal map. But the problem is this is pretty inefficient. Considering it's just a flat gray toilet, it's actually pretty darn expensive. So what we're going to do is we're going to make a new shader. I've already made one. I made it yesterday. But we'll do the same thing. I want to do something really cool with it because there's some really cool things you can do with shaders. It's not just putting pixels on toilets. Like you can do some seriously amazing stuff, especially with displacement maps. I'll show you a couple of examples just to kind of prime you for the kind of things you can do, and then we'll do something not the same because I'm not a godlike graphics programmer, but I'll show you what kind of things I do. So this is on the Unity. This is on a Unity blog of some people doing some cool shaders, animated materials. So the cool thing about shaders is that you can animate things really performantly. Like for example, if you want to make something like fantastic, my internet is dying. Let's just wait for that. Yeah, if you want to do some animation, like see this scene here? We've got like waves and stuff like that. That'd be how would you even approach programming that in Unity? You'd have to have like some sort of a mesh that deforms based on certain periods, and you have to have it like going across the whole mesh, and the mesh would have to go through things, and like that sounds really terribly complicated. Or you could use this and just make a shader that does it 10 times as efficiently and 10 times easier. Let's wait for this internet to actually catch up, and I can show you what it looks like. Holy moly. Well, anyway, it's taking forever to load. But basically, you can see like all the waves are rippling. Like this is just a flat plane, and it's the shader that's making it look like it's deforming. It's called a displacement map, and you can do some seriously cool stuff with it. With just a little knowledge about how shaders work, you can do stuff like that, and it's all done in the shader. Like none of that is done with a C# program. This is done in Unity just with shaders. And there's some like other examples, like you can do stuff like this is a flag, and this dude just has settings for how like much the flag waved. This is just a flat plane with some rips in it, and he has a special flag material that's like making it wave in the wind according to his parameters, and this is all done on the GPU, so you don't have to make some silly C# program that like stretches the flexible mesh and gives you like all this weird like cloth simulation stuff. It's all done on the GPU and it's all performant. So if you see cool stuff like that, it's really not that hard to do things like that. Like these are done with shader graph, which I don't know anything about, but that's basically it's an equivalent. I'll show you what a picture of it looks like. Shader graph is basically it's Shaderlab, except you can do it visually. Here's some of the thing. Yeah, so Shaderlab is the language. What these guys are talking about, shader graph, is like a graphed version of Shaderlab. So you can make shaders visually. So you can like add textures and then just have like just logic lines to different other parts of it, just so you can do things visually, because Shaderlab looks kind of drab. I'll show you. We'll make a shader and I'll show you what it looks like. So what you do to make a shader is right-click, create. What kind of shader should we make? Let's make a standard surface shader. I'll call it toilet 2. I've already made one, so there we go. We made a shader. So it gives you some basic code inside this shader. Fantastic. Sorry guys, this is just really slow. Yep. They're pretty sweet. I've used a visual shader thing in Unreal Engine. It was really nice. But you can do this just as good. So, well, open a new one. Sorry, this is just taking a long time to load. My computer's really slow. Pardon me? Not really. I'm not that. I don't know. All I know is the Unity side of that stuff. So I worked with a lot of people that did art things, and I had to put them in Unity. But I don't know anything about Blender really. I'm not really a 3D guy. I just know how it works enough to be able to use it in Unity. So this is one that I just made. So it's got all this stuff in it. This is just basic stuff. So it's got. I can't really show you the exact, like, what all this stuff exactly does. This is kind of a bit over my head, but I know enough to change what I want. Like, for instance, I don't think this toilet really needs a metallic portion to it. So I'm going to remove that. I'm going to remove this half metallic. That's the instantiation of that variable. And I'm going to remove this metallic thing. There we go. I'm going to save it and see if it compiles. Beauty. And then so I can make a new material. If my thing ever loads. And we'll call it Toilet 2. Matte, just for no conventions whatsoever. So Toilet 2 matte uses the standard shader by default, but we'll just change that to Toilet 2. There we go. And it's got everything, but also notice my metallic slider has been removed. So if you don't need the metallic part of it, we just made our own, and this is much more performant. So now I'm going to drag this Toilet 2 material, and now it doesn't have, hopefully it doesn't crash my computer. There we go. So now it doesn't, see, it almost looks exactly the same for our purposes. It's still got the smoothness, so we can still change that if we want to. But otherwise it's the same. We'll add a texture to it. Oh, these are horrible. Sure, why not? There we go. Doesn't look that much different than it did before, because it's just such a simple thing. But let's do something a little bit crazier. Let's say we want to do something a little bit like, you know, what that flag thing did. Let's see if we can. Let's scroll. I want to scroll. So what I mean by that is I want to scroll the texture UV. So the UV is kind of like what tells what parts of the texture to render where. So if it's a toilet texture, you obviously have like a UV and all that kind of stuff that, you know, like the toilet handle is going to be different from the rest of the bowl and all that stuff, like where the colors go and all that kind of stuff. But we can do some cool animation stuff that's really neato with Shaderlab. So what do I need to do? I have something prepared for this. So I'm going to make a property called scroll speed. So this is just a vector 4 basically, and I've got some predefined variables in there. And so that's going to determine how fast it scrolls. Render type opaque, yeah, that's all good. I have to also make a variable for it. So I'm going to make it a float 4. And I will call it scroll speeds. There we go. So I've instantiated it. And then what do I have to do? So, oh yeah, here we go. So this is the texture. So basically I'm applying the texture here. But what I can do is the second one, I've got the UV of the main texture. But what I can also do is I can add scroll speeds to it. Whoops. And then I can multiply it by something that's just inherently in all shaders, which is time. And I think that's all I need to do. So I've only added a couple of lines, and this is just some things you can look up, like scrolling textures is a pretty simple thing to do. And let's see if this actually worked. I think I typed in something wrong. Got it? I think I just started it. And 43. That'll do it. Scroll speeds. There we go. I forgot a R in my variable name. Let's try it again. Whoa! I'm getting mega lag. So it's like scrolling. So the texture is moving. But it's like doing stuff like that with code is really expensive, but you can do stuff that's like way like this is just a simple example. I only changed 3 lines of code and you could do all sorts of weird stuff. So just be aware that shaders are extremely powerful. And they're really awesome, so you should check them out. They make your whole... Go ahead. Oh, yeah. You should take it. Take it. Pretty simple stuff, but like there's so much stuff you can do. Like there's things like displacement maps, where you can like bend the mesh. It's just so cool. There's so much cool stuff you can do with shaders. They are not talked about enough, but they're really cool. So this is a simple example. I don't know. See, like I could do weird stuff like that. This is sorry, my thing is running at about 3 frames a second, but there's like all sorts of weird stuff. Like something I'd like to do is, if I can find it, there's a scary dude over here. He doesn't have any textures. He's just got just regular shaders. So it'd be kind of cool to like give him some textures. And give him some weird... Oh, I fell down. Anyways, he's just a gray dude, but like giving him some weird moving textures would be a really cool thing that doesn't cost a lot in terms of performance, but it just adds a lot of cool stuff. It's just another tool in your toolbox, right? So I think that's about it. Um, that's kind of what I wanted to talk about. The big stuff being um, the heap um, and the stack. Oh my god. Sorry, my computer is totally eating it right now. Um, and the profiler, and then just talking a little bit about shaders and what they can do, and the limits that are endless. So thanks for coming to my TED Talk. I appreciate it. Um, and that's really all I had to say. Is there any other questions about any of the stuff we talked about? Uh huh. Mm-hmm. Uh huh. Uh huh. That's a good question. I don't really know. I've never actually imported things from Blender. I don't know if you because you can import the shaders from Blender, but I don't know if you can modify them like as shader files. Like as Shaderlab files. Um. Uh huh. Yeah, that'd be cool. I'd be interested to know too. Um, because I know you can make shaders in Blender and then export them. But I wonder if you could modify them once they're in there, like once they're in the program, or wonder if they're just like static shader files. Um, yeah, because then if you want to do stuff like this, like obviously you can't do like scroll speed times time, probably not in Blender. But if you wanted to have that, basically the pipeline would be like they make a basic shader in Blender, they export it, and then you modify it, add the scroll stuff and the other textures, and then do that all in Unity, I guess. Build all the shaders in Unity. That's probably what I would do. Or just replace the textures entirely, because usually, like they're usually just standard shaders. Like it's just like a bump, it's like a normal map and then a like a whatever. It's like a couple of normal maps, or just textures and whatever. It'd be cool to um, just take that and then just throw it away entirely and then just build your own with exactly what you want. Like if you want to have scrolling textures or anything like that. Yeah, that is really good to know. If anybody has any other questions. Mm-hmm. Sure. Actually, I could probably do that now. I'll show you exactly what the profiler looks like in action. Sure. So the profiler it's just like another window, just like the scene in the game and all that stuff. You just right click and go, whoops. add tab, and then profiler. That's how you get the profiler, and then it looks like this. That's got a bunch of stuff. Oh, let's turn them all on. So, uh-huh. Uh-huh. Yeah, so it is a big part, but I'll teach you how to dig down into it. So to run the profiler, you just press play and then get ready to press pause, so that you can have a look at like a chunk. This thing is really frickin' slow, so. So usually these things aren't as high as that, but that's just the way it is, because my computer's so dang slow. But you can turn off certain things and see which things are causing a lot of issues. Let's just turn everything off except for garbage collection. We can see that we don't have any garbage collection lines. Must not have been on for long enough. But anyway, this is like an indicator of how well your performance is doing. Clearly on my computer, while I'm running OBS Studio and all this other stuff, it's not doing so great. But what you can do is, if you're usually all that stuff in the others category is inside the player loop somewhere. So it's something in here. It's like it could be the physics engine, it could be colliders, it could be anything like that. So you can dig down in here and you can see like what is taking all the time. So you can see, just as a overhead view, clearly the editor loop is taking a lot of time. That's probably because I'm running the profiler. Oh no, the profiler's down here. Whatever the editor's doing, it's got a lot of overhead. So that's using 88 milliseconds. That's why my frames are so low. A frame is usually like 23 milliseconds, so this is like taking up like 4 frames of time. But in my player loop, which is what's important, actually you can see like most of it's gone now that it's just my player loop, right? Like most of it's just my editor overhead. But you can see, you can dig down and be like, okay, 23 milliseconds, that's pretty long. What's making up the biggest points? Like, ooh, physics fix update, physics processing. So that probably means, if this is a huge component of this stuff, that something is taking a long time, like something in the physics is taking a long time. So what could it be? It could be a lot of stuff, but my guess, whoops, because I've built this thing, is I know that that enemy dude has absolutely massive and really complicated collision systems for no real reason, because I haven't really optimized it. So this dude, wherever he is, I could dig down into him and I can find, like, this is just a detective game. So this enemy's got armatures. So look at all those colliders in there. Like there's cube colliders and capsule colliders. Maybe it's something to do with this that's causing the issues. So basically use the profiler to sniff out these kinds of issues. This is a pretty simple example. Something that's more obvious is maybe like if you start digging down to these other stuff, you can start to find like assemblies and specific things that are actually doing things. You'll eventually find, I don't have any like really complicated programs in this, but like you'll find specific files that you wrote are really performance heavy. They're using up a lot of resources. Things like in this example, the drawing for the camera, that's kind of expected. It's got to draw pixels onto the screen. Something's got to do that. That takes a little bit of performance. But this is just basically, you just go down to all of these, and the overviews are pretty descriptive about what they do. So you probably, and if you can't Google it, you should be able to Google most of these things. So if something is taking up a lot, like the physics fixed update, someone online can tell you what that means, even if I can't. It's probably something to do with the physics engine. That dude's falling. He's got lots of colliders. It takes a lot of processing power to figure out what's doing that. So So be aware that the error loop takes up a lot of overhead, but you just ignore that. What you really are looking at is like the player loop. You can also look at a timeline. So this is really useful because this is like a whole frame. So this is really helpful when you're figuring out GPU and CPU bound stuff, because some things are going to wait for other things, and this is really good to see how that works. So you can see, like, look out, like the player loop takes 15 seconds. 15 milliseconds, and you can see what's taking the big stuff. So fixed update physics. Physics is taking up like a third of my time. Physics fixed update. Physics. It's all physics. It's got other stuff on here that are running in parallel. Physics, so there's fetch results. That's just all sub stuff for the physics engine. So clearly my physics engine is working a lot. Maybe there's something I can optimize to make that work a bit more efficiently. There's lots of parts to the profiler. There's memory, audio, all this stuff, physics. That's maybe something you could do a deeper dive into. Something that you might want to check out. Most of the time, I use the hierarchy. Like when I'm using the profiler, this is what's coming up first, because the things I'm looking for are GPU calls. That's like batches of like stuff to render, or specific calls to whatever's processing it, and then the GC allocation and how long it's taking. So the GC allocation is your garbage collection. It's like how much is the garbage collector working on this. These are pretty low. 6 kilobytes, 300 bytes. I've had programs that I've seen gigabytes on here for some of my bigger programs that we were doing really, really big data stuff in and visualization. So that's the kind of stuff you want to watch out for. Like, is something using megabytes when it's not doing anything at all, or it's not improving your experience? That's all things to just keep an eye out for. And as you use the profile, you just get used to knowing what kind of things are causing issues. And this is just so you're not going in blindly. Because if someone just says, just profile it, or not profile it, someone just make this work better. This is running at 30 frames, make it work at 60 frames. If you don't have a tool like this, it's impossible, I don't think, because you never know what you don't know what's causing the issues. But this basically tells you straight up exactly what's causing the issues. So that's how I use it. I'm basically on the hierarchy view. I don't know what raw hierarchy is. And then if I need to, I use the timeline and dig down. I wonder if I can get a better example, because this has a lot of stuff that's just like things you can't really remove. Like, you can't really remove the camera render part of this frame. But actually, this is a pretty performant program because there's almost nothing in it. But things will start popping up in here that you can start chopping out. Like, here's one that you definitely could remove. Log string to console, that's a debug.log, basically. Like, that takes like almost a millisecond. But like, once you start shaving milliseconds and milliseconds and milliseconds off, it makes a huge performance impact. So this is really good stuff to just check out and just dig deep and like see enemy controller update. So I even know where that is. So in the update behavior script, I'm controlling my enemy. He's not even doing anything right now. He should not be using this much performance. He should be he's standing still, not doing anything. Maybe he's doing this too often. Maybe I should change his update loops to only happen like every 4 updates, you know, because AI and like controllers like that are really expensive. So maybe I should make them a bit less expensive, because will it actually affect it if he checks every 4 frames instead of every frame to see if an enemy's nearby, so that he can start chasing you. Yeah, I think that's a good place to start, and super simple too. So those are the kinds of things I think about when I'm starting to do like performance passes. Is like, what's causing the issues first of all, and what can I get away with? So if I dig into enemy controller.update, what if I can open it from here? Nope, no luck. Enemy controller. Let's open it up and see if we can find what's causing all the issues. So it's happening in the update. So something in update is really not performant. Ignore this. I don't know what is going on here. So my update, if health less than 0, return. That's pretty bad. set float, and debug.log distance. So I'm making a new vector3 on the stack, because a vector3 is an object. Oh no, it's a float. Float.distance. Oh, I see. It's the distance between 2 points. That still makes something on the stack, because this has to create itself, and then it's got to decide how far that is. So it's still making a float and a vector3 on the stack. Sorry, on the heap. And then it's making a debug log every single frame for the distance. And that's taking up about a millisecond of time just to do this one thing right here. So debug.log only works with strings. So if you put something that's not a string in there, it just converts it to a string. So it's using all this extra heap performance. So that's something I could improve on. Probably should just remove this entirely because I don't need this in here. It's not required. That would increase the performance. I could probably write this in a different way so that it doesn't put so much stuff on the heap. But this is probably fine. After I do that, I could probably save this and try it again and see if it changes anything. Whoops. I'm going to crash, aren't I? I saved the script while it was still running. Pro tip, don't leave it running while you go to modify scripts. It will crash. Oh, never mind. Didn't crash. Nice. I don't see it. Doesn't mean it's not there, though. There we go. Look how tiny enemy controller is. It's like, it's 0.05 milliseconds. So I shaved almost an entire millisecond off just by doing that one, taking out that one line of code, for example. So basically that's how I do my iterative process. I come here, I see the big things. This is looking pretty big. Well, animators.update. Actually, maybe I could actually modify that so it doesn't update every frame. You probably don't need it to. And maybe I can have it just turned off unless, you know, the dude is a certain distance away. All these things make improvements to the performance. So that's kind of how I use the profiler.